Hello everyone, welcome to Mechanical Engineering online classes, MIOC. This is Shravani Sriramoju. Analyzing a mechanism often involves study of motion and forces. For forces, whether push or pull, result in motion. So studying forces is an inevitable part of analysis of mechanism. We know that an unstopped force can accelerate a mass, and this can be related as force is equal to mass multiplied by acceleration. So we can find force from acceleration it produces, and acceleration is velocity dependent. So velocity analysis becomes a prerequisite to acceleration analysis, which is followed by force analysis. Since force, velocity, acceleration are all vectors, we can draw like force polygons, velocity and acceleration polygons too. But this requires knowledge of vector algebra. So let's start with how to draw any vector. Vectors, as we know, have got both magnitude and direction. When drawn on a paper, should represent the actual vector in space, where magnitude can be taken to scale. Whose magnitude is AB be acting at an angle, say theta, with respect to horizontal, acting right upward. Then it can be represented as a vector AB, which is at an angle theta with respect to horizontal, and the direction is shown with an arrowhead. This is the tail and this is the tip of the vector. So we read it as vector AB. Vector AB in the sense vector is from A to B. While the length of this line is taken to scale of AB. If suppose AB is 1000 Newton, I can take 1 centimeter line. 1 centimeter can be equal to 1000 Newton when it's a force. Or it need not be force, it can be velocity, it can be acceleration, any vector quantity can be drawn to represent direction and magnitude taken to scale. In case if vector is in the opposite direction, then this is read as vector BA. So by the properties of vectors, AB vector can be written as minus BA, because AB to BA lengths, that is the magnitudes, are same but the direction is opposite. Now in case if vector AB is representing velocity, then we can write it this way: velocity of B with respect to A, because we read it as vector AB, A to B, and velocity is B with respect to A, or simply VBA. Here it will mean that B is this word and A is this word. Now before we move ahead with the velocity analysis, we should talk about types of motions. The types of motions is, one is absolute motion, the other is the relative motion. So if you do not know types of motions, the link is provided in the description box, or you can click on the I here. But to be very frank, all the motions are relative, since nothing is stationary. Things move relative to each other. But generally, we take Earth as a fixed reference plane, and every motion relative to Earth is termed as an absolute motion. Now, let us consider a case where if this van moves in a particular direction, then the motion of this van is referred to as the absolute motion of the van, or the motion of the van relative to Earth. Now suppose there's a child who is moving inside the van. Then the motion of the child will be described in two ways. One is the motion of the child relative to the van, which is nothing but motion of the child assuming the van to be stationary. This is first thing. The second thing is motion of the child or absolute motion of the child or motion of the child relative to earth is nothing but motion of the child relative to the van plus motion of the van relative to earth. That is, if VAO is a velocity of A with respect to O, and if VBA is a velocity of B with respect to A, then VBO will be the velocity of B relative to O, as VBO vector will be equal to VBA plus VAO. So this is the vector addition. Or for example, if you want to write it graphically, if say this is the vector VAO, there is some other vector, say VBA from A to B, then we can join them. The first vector's head can be joined with the second vector's tail. So we can draw this as VAO. This is from O to A. So this is O and A. So this A starts here. So keeping the same magnitude and direction, we can write this as B. This is VBA. Then the closing side of the polygon, this will be VBO. VAO plus VBA will be equal to VBO. So this is the vector addition. So any number of vectors can be added in a similar fashion. For example, if we have a vector from A to B, let this be VBA. Now from B, if there is some other vector from B to C, let this be VCB. And there is some other vector, say from C to D, so let this be DC. If there is another vector from D to E, this is VED. So the summation of all these vectors can be added to form a polygon like this. So the final will be something like this. So it's A, B, C, D and E. So this is VBA, VCB, VDC and VED. The closing side of this closing side of the polygon will be the resultant VEA, such that VEA is equal to sum of all these vectors. So here, if all these magnitudes are representing velocities, then yes, this the resultant velocity is sum of all the other velocity vectors. But this vector can be anything. This holds true for vectors. V need not be always velocity. It might be force, it might be acceleration or any vector. Here we are considering velocities. So velocity vectors we are dealing with. So the magnitude of the resultant velocity is the summation of the rest of the velocities. And here, before we add up this, we have to be very sure that when we are taking these velocities or vectors in order, the first vector starting from its end to head, the second vector's tail should be the first vector's head. Again, when it is VCB to VDC, this is the head of the second vector. This is the tail of the next vector, that is the third vector. So these should be in order. It cannot be like this. And you cannot say this is resultant or this is resultant. No. All of them should be in the same order. If at all there is A to B, then the next vector should be from B to C. It cannot be from C to B. If it is from C to B, then you cannot add. Alright, so when we are doing the vector addition, we have to be sure that all the vectors are in order. They are all in the same flow, in the same direction. The head of the first vector should be at the tail of the second vector. Here also the head of this vector is at the tail of the next vector, and so on. Then the closing side, if you see this is the last vector, it is downward towards E. The closing vector will be from the end of the first vector to the head of the last vector. This will be the closing side of the polygon, which will be the resultant of the rest of the vectors. So here from this we mean that EA vector is equal to ED plus DC plus CB plus BA. These vector magnitudes or the lengths. Now let us see the vector subtraction. As I told, if they are in the same flow, then they get added up. Now what happens if they are in opposite directions like this? One is here, one is in the other direction. Means the tail of one is touching the tail of the other. So in such cases, say this is point O. There is a vector A like this. So let this be VAO. And if there is another vector whose tails are touching each other, they are not head to tail, they are tail to tail. So if this is B, say this is VBO, then the closing side will give us VBA, which will be VBO minus VAO. If we are finding the resultant of B with respect to A in this particular case, we can find VAB also. In that case, our resultant will be towards A to B, suppose. Then we will get it as VAO minus VBO, or otherwise also we know that VAB is equal to minus VBA. So you can find the resultant. Velocity of B with respect to A can be found. Velocity of A with respect to B also can be found. So this is the vector subtraction. And now here velocities, these are just the vectors, right? So BA is equal to BO minus AO. These are the vectors, these lengths. Similarly, AB length will be equal to AO minus BO, because BA is equal to minus AB. So minus of this will become this one. Depending on the type of motion, we have two types of velocities. For linear motion, it is a linear velocity, rate of change of displacement. For angular motion, it is angular velocity, which is rate of change of angular displacement. Now, in kinematic analysis, velocities of various links can be determined by any of the following methods. The first being relative velocity method, this is also called as velocity polygon method. The second method is instantaneous center method. The third method is auxiliary point method. The fourth one being analytical method. And there can be even more types of methods, but these are the most important ones or the most used ones. Finding velocities in analytical method is already known to us from our intermediate physics or BTech first year engineering mechanics. The kinematics part, that is all analytical only, using formulae, using different expressions. We have the velocities are calculated. Even instantaneous center method is also learned in engineering first year of engineering mechanics. In this lecture, we shall stick to relative velocity method or velocity polygon method. Let us consider motion of a rigid link OA of length R, which rotates about a fixed point O with uniform angular velocity omega radian per second in counterclockwise direction. So for a small time interval delta t, let the link OA turn through a small angle delta theta. Then A will travel along the arc AA dash Then velocity of point A relative to O, if we denote it as VAO, this will be equal to the distance traveled by point A divided by the time t. The distance traveled by point A is the length of arc AA dash, and time is delta t. So we know that the length of arc is, since this OA is r, this arc length will be r into delta theta. So this is r delta theta by delta t. This is the velocity of point A with respect to O. Now if limit delta t tends to 0, then VAO can be written as r d theta by dt. As we know, d theta by dt is nothing but omega. So we can write VAO as r omega. Now if we carefully observe, the direction of velocity of A with respect to O, VAO, will be along the displacement of A, because as delta t tends to 0, that means when the time that we are taking is infinitesimally small, that time A dash will not be somewhere far away here. A dash will be somewhere very much near to A, somewhere here. And the line joining A dash will be a straight line, or it can be assumed to be a straight line, and will be perpendicular to the link OA. So therefore, the velocity of A, which is omega r, is perpendicular to the link OA. So this can be represented by a vector whose length is r omega and the direction is perpendicular to the link OA and is acting leftward because the link is rotating in anti-clockwise direction. The velocity vector can be represented like this. So it is the velocity vector of A with respect to O. It is, this line is taken perpendicular to OA link. These two are made perpendicular, and the length of this, which is the magnitude of the velocity, is taken to scale. For example, if we solve for r into omega, if r and omega values are given, and if the velocity has come out to be some 50 meter per second, that time I can take some 5 centimeter line. So drawing this configuration diagram first, we will take OA link as given. If it is given perpendicular, we will take like this, and the velocity of A with respect to O will be a horizontal line which will be perpendicular to this link, and of length say 5 centimeters, such that 1 centimeter is equal to 10 meter per second. So we can take any convenient scale. The direction must be shown. Now in case if we want to find the velocity of some other intermediate point on this particular link, say point B here, such that OB is of R1 length. So we can locate this B here, OB will be R1, and after delta t time B will be at B dash. So like how we found VAO, we can also find VBO. The only difference being VBO will be this length R for OB is R1, and omega is still the same, it is constant. So with this magnitude we can locate position of B, and we have already discussed that VBO by VAO will be equal to OB by OA, because these are velocities, so we are calling them velocity vectors, but this might be some other vector also. And how are we going to plot them onto a diagram? Only by taking their magnitudes. So this R omega is the length AO, so this R1 omega is length BO. So if R1 omega by R omega will be equal to BO length by AO length. Or we shall put it this way, OB by OA. This length OB by this length OA is equal to, what is OB? OB is nothing but omega into R1. What is R1? R1 is OB, capital O, capital B, the length of this line segment from the configuration diagram. And AO is, or OA is omega into R. R is nothing but the length of this OA. So OA. So this means OB on the velocity polygon and divided by OA, which is again taken from the velocity polygon, will be equal to OB by OA on the configuration diagram. That means point B divides the velocity vector the same ratio as that of the link. So drawing the given mechanism to scale, that is, if OA is given perpendicular to horizontal, then we will draw exactly perpendicular. Whatever length is given R, that we will be drawing to scale. The such figure is called as configuration diagram, and from which we have drawn velocity diagram or velocity polygon. Here we should remember one more point. The point is that whatever velocity diagram we have drawn so far, that will represent the velocity of point A only at a particular instant. Now because I am assuming that OA at this particular instant, the link OA is vertical. So because velocity will be perpendicular to it, we got a horizontal velocity polygon. This is horizontal, this vector is horizontal. In some other instance, say when OA is inclined with respect to horizontal, it is, say, making some angle theta here. That time this velocity will be perpendicular to this link. So that time we will have our velocity diagram which is perpendicular, and if this particular link is rotating again in anti-clockwise direction, that time our vector will be acting downward, perpendicular to the link. So depending on what instant it is, the velocity diagram will change. This is not fixed for a given link. This is fixed only for an instant when a link is there. So when OA assumes some other position, the velocity vectors also will change. The direction will change accordingly. Let us consider a quadratic cycle mechanism ABCD, in which AD is a fixed link and BC is a coupler. Let link AB be the driver that is rotating at an angular speed of omega radian per second in the clockwise direction. So we know that if we want to find the velocity of C with respect to A, then it can be found as the summation of velocity of C with respect to B plus velocity of B with respect to A. That will give us the velocity of C with respect to A. Now if we want to show the velocity vector of D with respect to A or A with respect to D, since A and D are not having any relative motion, there is no relative velocity as well. So the velocities that we are showing on the polygon, those lines are the magnitudes of the relative velocities. Now when the magnitude of this relative velocity itself is 0, then on the velocity vector polygon, the line will be of 0 magnitude. That means A to D distance is 0 in the velocity polygon. When the distance between A to D is 0, they will merge at a point. So the same point represents A and the same point represents D. So we have written the velocity of C relative to A as velocity of C relative to B plus velocity of B relative to A. So if V is velocity, then VC is velocity of C with respect to A. This is velocity of C with respect to B. This is velocity of B with respect to A. Since A and D represent the same point, velocity of C relative to A is nothing but velocity of c relative to d as well. So therefore we can write velocity of c with respect to d as velocity of c with respect to b plus velocity of b with respect to a, because these two will be same. Or on the diagram it will be dc length, the vector will be equal to ab plus bc. Let us construct the velocity diagram. Since we know the first vector AB completely, let us draw AB vector first. To draw AB vector, we know how to draw it. I am aligning one of the perpendicular scale to this link AB, and I have to draw perpendicular line to this link AB that will represent this B. So this AB vector is perpendicular to the AB link, and the length of this vector is to scale with the magnitude of the velocity of B with respect to A. So now let's draw the vector BC from B. So we will take the direction of link BC and we have to draw from B a perpendicular to the link BC. So I've aligned the scale to BC. So since these two are perpendicular, line drawn along this scale will be perpendicular to this link. So through B, I'm drawing a perpendicular line. Since we had omega of AB link, we exactly know the length of this vector, but we do not know other velocities. So randomly we have just known that we just know the direction, and along the direction we have drawn simply a line. We do not know what length it will be. And we also do not know whether the C point will be this word or that word. So a convenient length we have drawn on either side of B. Let us now draw a vector that shows the relative velocity of C and D. So D point is here, CD link is here. So perpendicular to CD link, I have to draw a line, a vector that is passing through D. So this is a vector that shows the relative velocity of BC. This is a vector that shows the relative velocity of C to D or D to C. So that means the intersection of these two vectors must be C. So this is the relative velocity of B with respect to A, and this is the relative velocity of C with respect to D or C with respect to A. Both are same. Now if you carefully observe, since point A and D are fixed, this particular relative velocity of C with respect to A and D, since this is fixed, this relative velocity of C is also the absolute velocity of C with respect to the fixed end. But yet we do not know whether the relative velocity the direction of BC is towards C or B. That is yet to be known. And this more because in this particular figure we can see that B and C, both of them are movable. So if at all we are finding the relative velocity of C with respect to B, then we will write it as CB, or in the other case it will be BC. Now we can similarly find point F on this particular vector. BC is here. So we know that FC by FB will be equal to FC by FB here also. So since this is all taken to scale, we have to find the ratio of F on BC, and accordingly we have to follow the same order on here. So based on that, our F is somewhere here. So if we join A or D to F, then that will be the absolute velocity of point F, because A and D are fixed. So this is how we plot the intermediate point, and we have joined to find the absolute velocity of F. Now there is another point in the mechanism which is offset to the mechanism. Now to write the vector equation for point E which is offset, we can write it as, in the vector form, velocity of E with respect to B plus B with respect to A will be equal to velocity of E with respect to C plus velocity of C with respect to D. That is, so the same thing is written in the vector form. Velocity of E with respect to B plus velocity of B with respect to A is equal to velocity of E with respect to C plus velocity of C with respect to D. So I just interchanged these two terms. I wrote it here and this here. This also I just interchanged them. There's no change. And on the velocity diagram, it will be vector AB plus vector BE, which should be equal to vector DC plus vector CE. So we will be drawing BE vector which is perpendicular to link BE. So I've aligned BE scale along this link BE. Now this scale is perpendicular to the link. So through B we shall draw a perpendicular to the link. Now we have to also draw CE. CE velocity will be perpendicular to the link this CE. So through C I am dropping a perpendicular. So this intersection point of these two velocities will be point E. So we know that AB plus BE is equal to DC plus CE. So the direction will be like this. A to B plus B to E will be equal to D to C plus C to E. And to find the absolute velocity of E, we have to join this point E with point AD. Since this point is fixed, so this particular vector along that joining A and E will be the absolute velocity of E with respect to A or D. So this completes our velocity analysis of a four-link mechanism.